That's interesting. I'm seeing all sorts of little people's names flying across the screen. It's very strange.
Oh, but I should introduce you again, Bruce. So thanks everyone for coming, and we're very glad to once again have Bruce Sagan going to continue to tell us about dynamical algebraic combinatorics.
Okay, thanks so much, Oliver. And I should say in this format, it's really hard for me to keep track of people's questions, especially if you put them in the chat or something. So you should just unmute if you got a question and ask. That'll be fine. And also I'm seeing all sorts of, are you seeing little names flying around the screen? I don't know what's
Yeah.
causing that.
Yeah.
I don't know how to stop it either. Anyway, I will just hopefully they don't seem to stay in one place very long, so hopefully
I
they
think,
won't cover up stuff.
Bruce, if you click the all eyes on me next to the icon, maybe
Oh,
we all
okay. All eyes
follow
on
you.
me. Is that in the upper right or where?
Yeah, but I'm not super sure.
All eyes on me. Clicking on it, but that doesn't seem to stop it.
Oh,
It doesn't seem to do anything, in fact.
my show, I'm following you, and so I don't know.
11 people are following you. Should I say stop presenting? That doesn't seem to.
I don't.
I think those pointy, yeah. I think those names that are flying around are for people's cursors and where they are, because this whiteboard you could write on it. This is like I could probably write on it.
I see. I see. So yeah, if you can manage to move your cursors so that you're not on here, that'd be great. Well, let's get started. So to recap, we defined row motion, and we saw that on a chain it was very simple. And so we looked for other more interesting and complicated things that we could do and looked at fences in some detail. Well, here's another way we can take simpler things and make more complicated ones. This is a very standard way of doing it, which is just by taking products. So if you've got two posets, P and then less than or equal to P, can people read that? It's really light here. Okay, good. And you've also got a poset Q and less than or equal to Q, then their product so, right, so there's going to be a bunch of ordered pairs, and we just need to tell you what the order relation is. So I've got one ordered pair, little p, little q, and I want to know when that's less than or equal to another little pair, little p prime, little q prime, and you do the obvious thing, you do it component-wise. So this just means that little p is less than little p prime in the first poset, and little q is less than or equal to little q prime in the second. Okay, so quick example just to make sure we're all on the same page here. Suppose I wanted to take the poset 0, 1 and take its product with this poset ABC. So then you would have pairs where the first component was 0 or 1, second component is A, B, or C, and the product would look like this. Right, so here this would be 0A. So on the bottom, we would have all the things with first component 0, 0B, 0C, and on the top, all things with first component 1. Right, so I have a copy of this ABC for every element in the first post set, and I have a copy of 0, 1 for every element in the second set. Questions about how you form this? Any questions? Okay, well, let's see what happens if we take a product of a chain with a chain. So let's look at 2 cross 2, right? This is going to look like a little diamond here. And just to make life easier on myself, I'm going to give, or actually, I don't think I even need to do that. That's the post set. And now let's look at the orbits of row motion. So let's start with, we can start with the empty orbit. And then remember, the way I do things is I just make these little dots really big if they're in the anti-chain. So let's see, what would be the next anti-chain, right? Take the lower order ideal, that's still empty. Take its complement, that's everything. Take the minimum element, that's just going to give me this. Everybody see that that's that. Good. Actually, let me see. What's going to happen next? Generate the lower order ideal, take its complement, and take the minimum elements. That's going to give me this. Do it again. It's going to give me the top element. Now the lower ideal is everything. So when I take the minimum elements, I'm back to 0. So what anti-chains didn't we get here? We didn't get this anti-chain. And you can check that when you do row motion, you get this anti-chain. And then it goes back. Okay, so this is what the orbits look like. So we have one orbit of length 4 and one orbit of length 2. Have we seen anything like that before? Yes, this is exactly the same orbit structure that we got for the bit strings of length 4 with 2 1s, right? So same size orbits as rotation on the bit strings of length 4 with 2 1s. You can go back and check. We had one orbit of length 4 and another orbit of length 2. So one could ask, is this an accident? Or is there something deeper going on here? And of course, the reason I bring up the question is because it's not an accident. There is a good reason for this. And again, this is getting back to this concept, which I've alluded to before, called equivariance, which we're going to talk about in great detail in the second lecture today. But for right now, it's just recognize that it's the same orbit structure as we had before for this different group action on this different set. Okay, so I just wanted to point that out. Any questions so far? Okay, great. So the way I'm going to, so I want to make this relationship between row motion on this cross product and rotation on these strings concrete. And in order to do that, I'm going to need to re-express row motion in terms of simpler operations called toggles. So that's the next thing that we're going to study. So just some got to give you some standard definitions from set theory to get started. So suppose we've got X and Y, or just any sets, doesn't matter. Then the difference X minus Y, it's just all the things that are in X which aren't in Y. So it's the set of all X in X, X not in little x in X, where little x is not Y. And if you like to think in terms of Venn diagrams, it's just this, okay? We're going to be interested in their symmetric difference. Which is denoted X and then with a little delta sign Y. And you take everything in X which is not in Y, disjoint union with everything which is in Y but not in X. So you can think of this, if you're into computer science, you can think of this as exclusive OR. It's the stuff that is in exactly one of the two sets, but not in both. And again, Venn diagram looks like this. Got all things in X alone or in Y alone, and that's that. Okay? Clear what these two operations are. Great. So some notes about these. First of all, there's this very nice property. If I take X and symmetric difference with Y, and then again do it twice. Take X as your base set and do symmetric difference with Y and do it again, I get back X. And secondly, this is the case we're going to be most interested in. What if Y consists of a single element? It's not hard to convince yourself that this does one of two things. It either adds Y to X if Y is not in X. So if Y is not in X, it gets added to it. And if Y is in X, it gets taken out. So this is what we mean by toggling. You either put Y in or you take Y out, depending on whether, if it was out, you put it in. If it was in, you take it out. Okay. These two properties of symmetric difference are really easy to prove, so I'm going to leave them as an exercise for this afternoon. Okay, but clear what symmetric what these mean, even though they need a little. Okay, so here's toggling. So now we're back to poset land. So let P be a poset. And suppose X is now an element of P. Then we're going to define the toggle map. Never remember which way the L and the E go on toggle. It's this way. Toggle map. So this is going to be a map denoted tau sub X, and it's going to be from the ideals of P to the ideals of P. And it's done as follows. So if I want to toggle X on an ideal, I take the symmetric difference of that ideal with X. Of course, this symmetric difference may not be an ideal. So I only do this if this symmetric difference is indeed an ideal. So if I can toggle X in or out and remain an ideal, I do so, and otherwise it's just fixed. So if I can't put X in or out and preserve being an ideal, I just make it a fixed point. Okay? Questions about this? Any questions? Let's do an example. That'll probably make it clearest. Let's take P to be this product of two chains. And I'm going to give these names so I can refer to them. Okay. And suppose your ideal, suppose we're taking the ideal that looks like this. Right? W and X. Let's compute some toggles. What will toggling, say, W, the lowest element, do to this ideal? Yeah, I think Aditya is shaking his head correctly. It won't do anything, right? W is this lowest element here. So I would have to try and take it out, but if I take it out, I don't have an ideal anymore. So it leaves the ideal invariant in this case. Everybody see why that's the same, that there's no change here. What happens if I toggle X? X being this element. Now what's going to happen? How many elements are going to be left? You can put, or you can just say, Aditya, you unmuted. Go ahead.
It will get removed because W is an ideal in itself.
Exactly. Now I can remove X and I still have an ideal, and so I get this. Let's now toggle Y. What's toggling Y going to do to this?
It will get added.
It gets added, right? We can add it. Yes, Robert. Also, you got it right. Right? This will get added because we can add it and it will remain an ideal. What about toggling Z? The top element. Nothing, right? You can't add, Z isn't in there. You can't add it and preserve the ideal property. So this will just stay the same. Everybody understand how toggles work? Is this example clear? Okay, so a few more things to note about toggles. Let's go back here. Some couple more notes. First of all, one nice thing about toggling is that it's an involution. Its square is 1, where here I'm using this as the identity map. So if you toggle twice, you get back the ideal you started with. Notice this also implies that T of X is a bijection, right? Because it has an inverse, namely itself. Again, this is not hard to prove, and I've put it on your exercises. So, and then there's just a bit of notation. As usual with functions, we have to tell you whether we're composing functions right to left or left to right. So we're going to compose toggles and any other functions right to left. So opposite from reading order. That is to say, if I write T of X, T of Y applied to some ideal, this means you do T of Y first and then T of X. Okay, it's just convention. Okay, well, I want to relate this now somehow to row motion. How am I going to do that? Well, I need one more concept.
Can we rephrase these rules as a covering relation somehow?
Yes, they're very, very intimately connected with covering relations, and that's actually a problem. Very good question, Aditya.
Okay.
On the problem set,
Oh,
and the crucial thing is these T of X and T of Y commute whenever X and Y don't, neither of them covers the other. So actually we've got more relations here, which I haven't stated. When they cover each other, they need not commute, but when they don't cover each other, they always commute. So yes, they're intimately connected. Other questions? And like I said, this is on your exercises. Okay. So here's the last thing we need to connect with row motion. So it's, again, this is a usual definition, which a lot of you will already know. It's the definition of a linear extension. So a linear extension and I will just abbreviate that to LE of a poset P with less than or equal to P as its order relation. We're going to think of it as a listing of P's elements. So a permutation of the elements of P. Say that list is X1, X2 up through Xn, satisfying the following property. If Xi is less than or equal to Xj and P, then the index I is less than or equal to the index J. Another way of saying that is that if Xi is less than or equal to Xj in the poset, then Xi appears to the left of Xj in the linear extension, right? So you start with your linear extension with the smaller elements and then work towards the larger ones. Okay, so let's do a quick example. Again, we're back to this poset we've been using. How many linear extensions do we have here? 2. Yeah, exactly. Because of the fact that, right, since we're going from bottom to top, we have to start with 0, or the W here. And now we have a choice. We can either go X and then Y and then put the top element on, or we could go in the other order. We could do W has to come first, but now we could do Y, X. And then tack on the Z. Everybody happy with any questions? Okay. And we're actually going to need a reverse linear extensions. So a reverse linear extension. Or RLE is just an ordering X1 through Xn such that if you reverse it, X1 through Xn is a linear extension. Yeah, so they're just linear extensions read backwards. You start with the highest elements and go down. So the reverse linear extensions are just gotten by reading these backwards. So Z, Y, X, W, and CX. Questions about reverse linear extensions? Or linear extensions? No, good. This is pretty straightforward. So here's this amazing lemma of Cameron and von der Vlas in a really seminal paper that they wrote. So fine. And as I said, this is by Peter Cameron and von der Vlas. It's from a 1995 paper. And it says the following: take any reverse linear extension. So suppose x1 through xn is a reverse, sorry about that. Linear extension of a poset P. And take any ideal in P. Then if I look at row motion on that ideal, remember row motion can be either on anti-chains or on ideals. I'm doing the ideal version here, which I denoted by row hat. That is gotten by applying the toggles for this reverse linear extension. To I. So this, remember, this single operation of row motion can be gotten by doing smaller little bits by toggling. Now, this is an amazing, first of all, just that these two operations would be related. But second, notice this is for any reverse linear extension. So no matter what linear extension you pick, you always get row motion on the ideals. It's independent of which one you choose, which is also just kind of mind-blowing. Let's look at an example so we can see how this works. And use our usual example, right? So I is going to be, and remember this is W, X, Y, Z. And we're going to use, that's our usual poset, and we're going to use this as our ideal. So let's first do row hat. Remember how that goes. First of all, you take complement. That's going to give me this, right? Then you take the minimum elements of the complement. That's going to give me this. And then finally, take the down of that. You generate the ideal for that, which is going to be this. So this is row hat of I. So now let's use one of the reverse linear extensions. Say, let's use the Z, Y, X, W. Okay. So again, we start with my same ideal. And now we start to toggle. So we toggle with Z, first of all. When I toggle with Z, what happens? Nothing, right? Z, you can't add Z to this and get, so we leave the same. Now I toggle with y. What happens? Now I can add y in, right? Y to this gives me a nice V-shaped ideal. Now I toggle with x. X is in the ideal. Can I toggle it out? It's this left-hand one. Yes, I can toggle it out. Finally, I toggle with W. Remember, W is the minimum element here. Can I remove W and still have an ideal? No, right? This bottom element you can't remove. So therefore, it leaves it alone. And lo and behold, this week, right? Totally different sequence of operations, and yet I get the same output. Quite amazing. Any questions about how these toggles work and how they relate to row hat before we look at a proof of this lemma? Questions? Okay, so to prove this, let's see, I think. We're going to set up some notation just so I don't have to keep writing it down. Let J be the result of applying row hat to I. Okay. And now here's the key. I'm going to, right, the toggles are going step by step. I'm going to give you another way of doing the same step-by-step operations. So for I equals 0, 1 up through n, we're going to define sets J sub I as follows. J sub I is you take J, the result of row hat, and intersect it with the first I elements of your linear extension. And then you take the union, which will in fact be a disjoint union, of I intersected with the last ones from I plus 1. Right? So you break these reverse linear extension into the first I, the last n minus I. You would intersect the first I with J and the second set with I. Okay? Weird. So let's take a look at what this looks like in the example we were just doing. Okay, so let's compute these J sub I's. So J sub 0, in J sub 0, everything is intersected with I, right? So you take the whole if you look at the definition, you'll see it's just I intersecting with the whole, all of the stuff. Right? Because when I is 0, well, let's go back so you can see. Right? What happens when I is 0? When I is 0, there are no elements, right? This is the empty set because it's going from x1 to x0. You can't, there is no x0. This is the empty set. And so everything is in this portion. When I is 0, you're taking x1 through xn and intersecting that with I. Okay. So this is I intersected with all of these guys. Well, that's just I. Clearly, right? Because this is the whole post set. Now let's take J1. What is J1? J1 now, the first element here moves over and gets intersected with J. And then you put that together with I intersected with the rest. Right? So I is intersecting only these three, and now the Z is coming over and intersecting with J. Well, what is that? So remember, this is J here. So that's J is these two elements, W and Y. And I is these two elements, X and W. So does J intersect Z at all? No. So there's nothing there. What about I intersect Y, X, W? It's still just I. It's still just X and W, or I if you prefer. Notice what happened after I applied the first toggle. I didn't change. Now let's look at J2. What is J2? J is now intersected with the first two elements of my linear extension. And now I is intersected with the last two. Okay, J intersects ZY. This was J. What does that give me? Y, exactly. What about JI intersected with XW? So here's I intersected with XW. That gives me what? It gives me X and W, right? These are the two elements of I. Everybody see this? But notice, what is YXW? YXW is exactly this poset, YXW. And this J1 was exactly this poset, and this one. What do you suppose you're going to get when you calculate J3? The next one over, right? This is going to be J3, and this is going to be J4. So these are two different, right? One way we got by toggling, the other way we get by doing these crazy intersections, but we seem to be getting the same thing, and we always do. And that's what the proof is going to show you. So let's go back to the proof now. So as we already noticed, J sub 0, right? When I is 0, you're only intersecting with I. So you're intersecting all of the things with I. Well, obviously, if I intersect all the elements with I get I. Let's look at the other extreme. What is Jn? Now what's happening? Now all of the elements are in this first set, right? I is running to n, so this is all the elements from 1 to n. And there's nothing here because n plus 1 to n, that's the empty set. But if I intersect J with all the elements, what do I get? J. So I start where I want to be, right? I start at I, and I end up at J, which remember J was by definition what happens with rho hat. So if I can just show this thing that we observed, that each of these JIs is given to you by doing a certain number of the toggles, the corresponding number of the toggles, will be done. And now we can do that by induction, right? Because we've got I to induct on. Okay, so we're now, so it suffices to show that JI is equal to TI for all I, where TI is just what you get by doing the first I toggles. Right? That will do it. Okay, so, and we're going to, as I said, induct on I. Okay, well, we already know that J0 is I, which is T0. T0 means do no toggles. So if we don't do any toggles, we don't change anything. So that's the base case. So we can assume that J sub I minus 1 is T sub I minus 1. And now we need to prove it for I. So let me write these out because it's going to be easier to see what's going on if I do. So what is J sub I minus 1? It by definition is J intersected with the first I minus 1 things together with I intersected with everything else. And what is J sub I? J sub I is J intersected with the first I ones together with I intersected with the rest, starting with X, I plus 1. Let's call that equation 1 so I can refer back to it. So let's look at J sub I, all the elements in J sub I except X sub I. So take X sub I away if it's there, and if X sub I isn't in there, this won't affect J sub I. I claim that that has got to be the same as J sub I minus 1 if I ignore X sub I. Why is that? Well, look at these two. This was J sub I minus 1 and this was J sub I. What was the only difference between these two intersections here? The only difference was that Xi moved from this set to this set. Everything else stayed the same, right? So there will be no difference. The only difference between J sub I and J sub I minus 1 is what happens to X sub I. And we're removing X sub I if it's there, so we're ignoring it. So this is by the equations. But remember, we can say that this is T sub I minus 1 minus X sub I. Why can I say that? We're using what famous hypothesis? Yes, exactly. The induction hypothesis, right? For I minus 1, we're assuming that these guys are equal. So this is by induction. But I claim that this is also the same as applying the toggle X sub I to Ti minus 1. Why is that? Well, think about it. What does this toggle do to Ti minus 1? It either leaves it alone, puts Xi in, or takes Xi out. But remember, we're ignoring X sub I. If we ignore X sub I, does the toggle do anything? No, because we don't care what happens to X sub I. So this is by definition of Tx sub I. But remember, what was Ti minus 1? It was doing all the toggles up through X sub I minus 1. So if I do that last toggle, this is just T sub I. So this is by definition of T sub I. So notice what we've shown. We've shown that J sub I and T sub I agree everywhere except possibly at X sub I, right? That's the only thing we need to worry about. So now it suffices to show that if I look, now let's concentrate on X sub I. If I look at whether X sub I is in J sub I or not, then that gives me the same thing as whether it's in T sub I, right? This will now take care of right? It's either going to be in both or it's not going to be in both, and will be done. And this, of course, we're leaving as an exercise. Now that you've seen this. So, and that is all I think I have to say this for this lecture. So thanks so much for listening.
Okay, so thanks, Bruce. As you can see, I've been actually watching this in VR. So we're going to take a 15-minute break, and we'll be back at, I guess, 11:01 or 1 after the hour, whatever hour you're in.
Right. Sounds great. See you then.